Good morning, everyone, and welcome to the third and final lecture of the Electron-phonon interactions in VASP workshop. Our speaker today is Henrique Miranda, who is one of the VASP developers and developed the Electron-phonon and phonon code. He did his PhD in Luxembourg with Ludger Wirtz and a postdoc in the University Catholique de Louvain-la-Neuve in electron-phonon calculations. He's going to take us through transport property calculations in VASP, including the conductivity, mobility, and ZT figure of merit. So, welcome Henrique, and the stage is yours.
Thank you, Chris. So as you just mentioned, I will be guiding you through new implementation in VASP that allows us to compute electronic transport properties limited by phonon scattering. So there are many interesting applications in electron-phonon physics, for example, superconductivity, spectroscopy. But today I will be guiding you about this particular case of electronic transport. This is also useful to study, for example, solar cells or electronics. So why do we care about transport? So the transport coefficients tell us how well the materials conduct electricity and heat. Large-scale systems are affected by microscopic scattering, and it's this microscopic scattering that we will try to describe and compute. One of the applications, why it's useful to study transport is conductivity, so electrical conductivity, particular case of metals, mobility for semiconductors, or the figure of merit for thermoelectrics. The particular case of metals, for power transmission, you need to transport energy from the point where it is produced, so the power plant, to our homes. This is done, of course, with metallic wires. And there is an electric field that makes the electrons move along this metal. But along the way, these electrons are colliding with ionic movements, or the fact that ions are moving, they are scattering electrons. And this is to energy loss, and this loss is heat. So as a little figure, between 5 to 10% of the generated power is lost as heat worldwide. So if we could find better conductors, we could lower this scattering and reduce energy waste. Just a little reminder, conductivity is just the inverse of resistivity. The typical units for conductivity is Siemens per meter, and the resistivity is ohm times meter. And so in terms of the best metals that we can have, so metals with lowest resistivity, this table is just taken from Wikipedia. Still the best choice we could make in principle would be silver, where the resistivity is very low. But of course, the cost forbids from using silver for electricity, from this scenario here. So usually one uses copper. Still, copper sometimes is too expensive, so in some cases, aluminum is used. It has a higher resistivity, but still the cost is beneficial. Of course, it is, so we are not going to find, it's unlikely that we'll find a better metal for this application, but in other applications, we might have different requirements, like different operating temperatures, or you might want to find a metal that has a certain different mechanical resistance. So it's still interesting to study metals. Another case is the mobility of semiconductors. So in that case, for semiconductors, we have a gap, and there the conductivity depends on the carrier density and how easily they move. So that's our mobility. The carrier density depends a lot on the doping and temperature. So of course, if we increase dopants, we are increasing the number of carriers, and the temperature also changes. Many carriers are available in the material. Why it is useful to look at mobility instead of conductivity is that the mobilities are roughly doping independent at low carrier concentrations. So this allows us to compare materials in a better way, saying under the same number of carriers, which material would be better at conducting electricity. Looking at the mobility, studying it from first principles allows to check what are the dominant scattering mechanisms, either they are phonons or impurities. And in this talk, I will focus exclusively on phonon scattering. Another application is thermoelectrics. So here on the right, we have Thomas Johann Seebeck, who was a German physicist, who in 1821 found that the temperature difference across two dissimilar metals can generate an electric voltage. And on the right, we have Jean-Charles Athanase Peltier, who was a French physicist, that in 1834 found that passing an electric current through a junction of two different conductors can create a temperature difference. So these are the two effects. So these two effects got the name of the founder. One use case for the Peltier effect is thermoelectric camping coolers. So imagine yourself, you want to go camping and you want to keep your food and drinks cold. You can use a power source. So for example, your car, you can connect this little cooler to your car and have an electric current flowing that transports the heat from inside the cooler to outside. So keeping things inside the cooler cold. The advantage of such cooler is that you don't need a refrigerant and no heat pump is needed. So that's portable. Imagine yourself carrying a fridge. That would not be very practical. Another case of an application for thermoelectrics is the Seebeck effect. The idea is to generate electricity from heat transport. So imagine the case you want to launch a space probe. That's a bit of a more ambitious goal than going camping. You launch this space probe to study the outer solar system, interstellar space beyond the heliosphere. Solar panels are not really a good option beyond Jupiter because the amount of energy that reaches Jupiter is already low. And you can just look, for example, at the specifications of the solar panels of the Juno mission. So they are quite big, these solar panels. And so that is possible still for Jupiter with modern instruments. But back in 1977, during the Voyager 1 and 2, power consumption was much higher. So solar panels were not so developed. That was not really an option at the time. And there, what they did was to come up with a nuclear core, and that is radioactive material that is decaying and emitting heat. And then they put these panels around of thermoelectric material. And because of a temperature gradient between the core and the outer part, that produces electricity. And that electricity was enough to feed the instruments of these space probes. And curiously enough, this was just done 150 years after Seebeck's discovery, which is quite impressive. So in this talk, I will guide you through different parts to be able to compute these properties from first principles. So in the first part, I will talk about the theory. So we will start with Boltzmann transport equation, Onsager coefficients, and the definition of these transport coefficients, and how we can determine the chemical potential under different temperatures and dopings. Then I will go into the details of the computation, so how we can do these calculations in practice in VASP, prepare a supercell to compute the phonons and the electron-phonon potential, perform the transport calculation. I will discuss the performance, so how to run these calculations effectively and efficiently. And finally, I will show you some actual results for these three use cases that I just described before. So without further ado, let's start with the theory. So the electronic transport coefficients, first we start by our observable. Those are electric currents and heat currents. For an electric current that is defined as a charge that is moving on the material. So this V and K is the electron velocity, the electron moving, the velocity of the electron inside the material. F and K is the electron occupation. So only electrons that are occupied can carry the electric current. And for the heat current, we don't have a charge, but we have an energy, and that is what is being transported. To look into this and to be able to compute these currents, we start by linearizing the electron occupation in terms of the Fermi-Dirac distribution, and we define an equilibrium part and a deviation part. That means we have a material, and then suddenly we apply an electric field or a temperature gradient, and we look at how this occupation changes. It can be shown that the equilibrium part vanishes, and in the end, the currents that appear in our material are only related to the deviation. And so that's what we need to compute. So that can be done using the Boltzmann transport equation. Here on the right, you have a statue of Boltzmann in the main building of the University of Vienna. And he came up with this equation that describes these occupations in the material. So we have our Fermi-Dirac occupation with static part plus deviation. And we have these two terms here. That one is the derivative in real space of the Fermi-Dirac distribution, and the other one is the derivative with respect to momentum. And we can combine these two expressions to rewrite the left-hand side of the equation, obtaining this equation. We also substituted the force by force due to an electric field, external electric field. And on the right side, we have the change of the occupations with time due to collisions. On the left side, the derivative of the occupation with respect to time vanishes. And then we can define an electrochemical potential. And we can use the relaxation time approximation to define a relaxation time and this deviation part of the Fermi-Dirac distribution. So we have a practical way now to compute this deviation in terms of equilibrium quantities and fields and temperature gradient. So going back to our currents, we substitute this deviation part, and we can define Onsager coefficients, which relate externally applied electric field or the electrochemical potential, this E, and temperature gradients to our currents. So this you can see like a little 2x2 matrix, L11, L12, L21, and L22, that transforms your external fields, electrochemical potential, and temperature gradients to electric currents and heat currents. So the Onsager coefficients can be written in this very short form that depends on the transport function, which is simply Brillouin's own integral of the group velocities with a delta function and relaxation time for particular electronic state. And then this transport distribution function, that is a convolution in energy with the derivative of the Fermi occupation energy. And depending on which little element of the 2x2 matrix we are looking at, we get a weighting function. So knowing these Onsager coefficients, these four Onsager coefficients, we can compute our electronic transport properties. So the L11 part is directly the electrical conductivity. We can compute the Peltier coefficient. We can compute the Seebeck coefficient and the charge carrier contribution to the thermal conductivity. So in the first case, it's really, we apply an electric field and we generate an electric current. In the other cases, we apply a heat current and generate electric field or vice versa. And in the last case, it's just how much heat the electrons can carry. So that's a contribution to the thermal conductivity. So how do we evaluate the Onsager coefficients? There are two ways that I will show you next. One of them is linear grids and Simpson integration, and the other one is Gauss-Legendre. The idea behind linear grids and Simpson integration is just, okay, we have an integral in energy, and we just discretize it. It's a linear spacing in energy between a minimum energy and a maximum energy, and we give some weights that are determined by the Simpson integration. So this integral that in principle would expand all the range of energies relevant to transport becomes a discrete sum between a minimum and a maximum energy. The number of points between minimum and maximum can be set in VASP with this incar tag. A lower n means, of course, lower accuracy, but a higher number for this particular case does not increase the cost significantly. What increases the cost a lot in this case is the energy window. So the minimum and maximum energy and how large they are around the Fermi level. And I will show you in more detail how this works. We can set temperatures in the incar using this variable, ELF self n temps. And to select this mode of integration, we use ELF transport driver equals to. So how does this work? ELF transport differential to set a minimum and a maximum energy. So as I just mentioned, the Onsager coefficients are a convolution of the transport distribution function with the derivative of Fermi Dirac distribution with respect to energy. And by setting this tag, we determine how much of an integral under the curve is discarded in the evaluation of the Onsager coefficients. So that is basically this part. And visually, this is the following. So the derivative of Fermi Dirac distribution with respect to energy is centered around the chemical potential, which here I set to zero, as zero. And the width of this function is related to the temperature. And by setting an alpha of 0.05, that means that we exclude 5% of the integral under the curve. And so the energy range will be determined by these two energies, 0.03 EV and 0.0. So negative and positive. Of course, as I just mentioned, with different temperatures, this window is broader, and accordingly, size of the window also. If we set a lower value for ELF transport de Fermi toll, so for alpha, then we see that the energy window increases. And this significantly increases the computational cost too. And I will show you exactly why in a second. You can continue to decrease this value of alpha and you see how it goes. So it just includes more and more of the integral. So your final result will be more accurate, but computational cost will also increase. This is the default. Now, the other method is Gauss-Legendre integration, and the trick there is to make a substitution, make it such that this integral is bounded between -1 and 1, and then one can use Gauss-Legendre integration to evaluate, to discretize the integral in energy space and evaluate it. And the advantage of this approach is that you only need to set the number of points that you want in your grid, and the energy window is automatically set. It's automatically determined by the xk points, and that come directly from the Gauss-Legendre integration. So these are tables, can be generated algorithmically, and they are done so inside. To select this mode of integration, one can use the incar tag ELF transport driver equals to 2. So as I mentioned it before, but there is an energy window, this transport energy window. How does this look like? So consider here band structure of silicon and between gamma and X. And what happens basically is that if you want to look at mobility of electrons, you only need to consider states around this energy region, and the size of this window is determined in the case of Gauss-Legendre by the number of points. Say you want to compute mobility at 300 Kelvin, so room temperature. If you have 51 points, then you get an energy window that follows this blue curve. And as you increase the number of points, the size of the window increases. If, on the other hand, you keep number of points fixed, let's say the maximum 501, also increasing the temperature means that the process, this transport occurs in a larger energy. So you need to consider the scattering between more states. Now, another important aspect is to determine the chemical potential. The total number of electrons includes additional carriers introduced by doping. So the number of carriers is equal to the Fermi-Dirac distribution with a certain temperature and your chemical potential minus this Fermi-Dirac distribution at 0 temperature, EF, that's just the intrinsic, and so the undoped material. So where the Fermi level will be. Choosing a positive number of carriers corresponds to n-type doping. And this is just because in VASP, the number of carriers means the number of additional electrons. So typically, one says n-type doping means a negative charge. That's just because so electrons have a negative charge. N-type doping means adding electrons. And negative carriers means p-type doping because holes would have positive charge. The carrier concentration is given then by this formula. So, I mean, if you just add a certain number of carriers, you can divide them by the volume of your primitive cell, and then you have a carrier. And this equation can be numerically inverted to obtain the chemical potential, knowing the carrier concentration. So I will show you what this means exactly. So first of all, the chemical potential determines where the vertical position of this energy. So if you increase the carriers, so if you add electrons to your system, then this window will move up. The same way if you remove there are different ways to set this mu in the in-car. One of them is to set mu relative to the Fermi level. So in the case of semiconductor, it will be somewhere here in the gap. And you can set a shift with respect to this Fermi level. And then you just set directly mu here in this equation, and you can compute your number of carriers and your carrier density. Or you can also set the carrier density and determine mu, and that is just by solving this numerically. So you need to find a mu that gives you the carrier density that you want. And carrier per cell, that's just the carrier density times the volume. You can also set a range of chemical potentials or of carrier densities. So you just need to append this underscore range. So you can do that for mu, and you set a lower limit, upper limit, and a number of steps, and you can set a range of energies. Say if you want to explore transport properties as a function of chemical potential or of carrier density, that is the most usual setting in an experiment. You can also set a range of temperatures, of course. The next step is to compute the electronic lifetimes due to electron-phonon scattering. That's the next ingredient that enters in our transport distribution function. We start to compute these electronic lifetimes. We start from the electron self-energy due to electron-phonon coupling. And that is just the sum of the Van-Migdal term with the Debye-Waller. So the Van-Migdal self-energy looks like this in terms of Feynman diagrams, and the Debye-Waller like this. Now, the Van-Migdal is a complex quantity and the Debye-Waller is a real quantity. The lifetimes are the inverse of the line width, which is proportional to the imaginary part of the self-energy. And what this means is that we don't need to worry about the Debye-Waller. We can only compute the Van-Migdal, and that is sufficient to obtain lifetimes. So how do we get the lifetimes from the Van-Migdal electron self-energy? So the Van-Migdal electron self-energy looks like this. We consider the on the mass shell approximation. That means we evaluate the self-energy at omega equals to the Kohn-Sham energy, or the eigenvalue energy. So we replace omega by the eigenvalue energy. And then we take the imaginary part, and using this relation, we obtain minus pi and delta functions. This gives us electronic lifetimes. And there is a little detail that somehow I omitted, but you can read more about it in this reference that will be available soon. That is different approximations that you can use to define your electronic lifetimes. And these different approximations can get you closer to a self-consistent solution of the Boltzmann transport equation. So, well, the lowest level of approximation that one can use is to simply not compute the electronic lifetimes and to just use one value. That's the constant relaxation time approximation. And it's has been used a lot, and it's been very useful for quick calculations. You can use that now inside VASP by setting ELF scattering approx in Cartag with equals to CRTA, and then you have transport relaxation time. Next is the CERTA approximation, and that comes directly from the Van Migdal self-energy. And in that case, omega is just equal to. So that's really just following the equations that I was showing you before. And you define your lifetimes from the electron self-energy. And there are two other approximations that are useful and used a lot in the literature. That is the momentum relaxation time approximation. And there are two commonly used forms that differ in the approximations or how the derivation comes about. In one of them, MRTA lambda, it is assumed that the mean free path is smooth in K-space, while in MRTA tau, it is assumed that the lifetime is smooth. It is typically the MRTA lambda is more numerically stable. There are two other approximations, that is the energy relaxation time approximation, but those we found that are numerically unstable, so we don't recommend to use. The electronic lifetimes, as I showed you before, there are two contributions. One of them is phonon emission, meaning we can think of it like this. We want to compute the lifetime of particular eigenvalue at nk, and we consider that it can emit a phonon. So that's this red process. So it loses energy, and the energy conservation is set by these delta functions, or it can absorb a phonon and gain and go up. Yeah. So apart from energy conservation enforced by these delta functions, there is an implicit momentum conservation condition that is somehow hidden here in this equation in the electron-phonon matrix element. But basically what it means is that it only makes sense to consider, because here we have three momentums, but there is always has to be conservation of momentum. So in fact, we have only two. So Q has to be equal to K minus K prime. What this means in practice, you can think of it like this. You define a mesh of points. In VASP, you can use a K-points file. It is the same file format as the typical K-points file you use for ground state calculation. And you set a K-mesh. The Q-mesh is determined automatically by taking differences between the K-points that you have. So one should use regular meshes, and the Q mesh is going to become the center, because you can always have a difference between K minus K. So you will get Q equals to 0. That is the gamma. One important note is that the computation of each tau at nk, so tau nk, implies a sum over Q. And this is what makes computation expensive. It's obtaining these electronic lifetimes. And that is why it is useful to have energy windows, is to select which tau nk we need to compute, and not compute more than what we will need to obtain our results. So that covers the theory. Now I will show you how we implemented this. Our design goals to create a reliable and robust implementation as typical in VASP. We wanted to make it automatic. So try to have just one input file that can work on different materials, to not have to tune specifically new in-car for every new material that we want to study. Sometimes we make a compromise in pure speed for this stability and reliability and being automatic. In that aspect, binarization is not a requirement, so we don't need to do binarization. It will be available in an upcoming release, but not in the current ones. This means that you don't need to deal with a binarization procedure. So the calculations are done in two steps. The first one, you need to do a supercell calculation where you obtain the phonons and electron-phonon potential. And the second step you can do in a primitive cell and you obtain the transport coefficients. So the supercell part, you just create copies of your primitive cell and you make displacements of the ions and you compute the derivatives of your Kohn-Sham potential with this ionic displacement. Then you want to obtain these derivatives of the Kohn-Sham potential in the primitive cell such that you can compute your electron-phonon matrix elements. To go from the supercell to the primitive cell, this is done through Fourier interpolation. So for each Q, you do a Fourier interpolation that basically folds your supercell into a primitive cell. And then the computation of these matrix elements is feasible. There are two workflows available. One of them is using just VASP. So you just set Ibrayon 6 in VASP, and VASP will do all the different displacements, one after the other. And at the end of the calculation, produce a FLL params HDF5 file that contains the derivatives of your Kohn-Sham potential in the supercell. The other approach is using FLL, which is actually what we used initially. So the original implementation of Electron-phonon in this way was done using FLL code that was developed by Atsushi Togo, also the developer of PhononPy. And the workflow is very similar to PhononPy. You create separate displacements and you run VASP calculations in these displacements, and this FLL code combines the information of these calculations and produces the same file, FLL params. So this FLL params goes into the second step of the calculation, where we do the calculation of transport. That part is, so you have this FLL params that contains electron-phonon potential. We need to do the computation of electronic wave functions non-self-consistently in the Brillouin zone. The electron-phonon potential, as I mentioned before, we need to do a Fourier interpolation to the primitive cell. We need to do the treatment of dipoles, that is the long-range part of the electron-phonon potential. I will not go into much details about this in this talk. The electronic wave functions are computed in G-Brillouin zone, but are expanded on the fly to the full Brillouin zone. Once we have the wave functions and the potential in the primitive cell, then we can compute electron-phonon matrix elements. With the information of the eigenvalues in the Brillouin zone, we can compute also the chemical potential. And we can combine this information to obtain the electronic lifetimes. Note what I said, what I mentioned already before. We only compute G, so electron-phonon matrix elements, when the delta function is non-zero. So before computing G, we look at this delta, which is very cheap to evaluate. And only if this is non-zero, then we evaluate G. So this also gives a speed up in the calculation of the lifetimes. So once we have the lifetimes, we continue with our workflow. And we can compute the transport distribution function that is just taking lifetimes, multiply them by the group velocities, and then integrate to obtain the Onsager coefficients. Again, here we only compute tau, which fall within the transport energy window. So this is another procedure that speeds up the calculation. And finally, when we have the Onsager coefficients, then it's trivial to obtain. The transport in-car looks like this. So one of the fundamental in-car tags that you might choose to set is ELF mode transport. And this tag controls some of the other electron-phonon tags and sets reasonable defaults, like, for example, all. So if you just set this tag in your in-car file, these are also internally set. You don't need to set them explicitly. And so you are ready to go. Now, I want to make a note about performance. These calculations can become expensive, yeah, and especially when we compute the lifetimes due to electron-phonon scattering. Remember that each lifetime at nk implies a sum over q, so it can really become expensive. It's important to converge carefully the calculations. So look at these three input parameters because they can really change a lot how fast your calculation runs. I will show you in detail how much. So the strategy should be run small convergence tests. Pick the smallest values that stabilize the target quantities. You will be able to run these calculations in hours instead of days, and you will be able to save a lot of memory. So the particular example I will show you is this one, and it's the computation of mobility. One of these in-car tags that impacts performance a lot is ENCAT, and that determines the plane wave cutoff for the electron-phonon potential and the FFT size for the orbitals. And in this table here, I show you different values of the cutoff and the final mobility that we get after calculation. And I show also the error with respect to the value with highest cutoff and the computational time and the speed up and memory. So as we can see in this calculation, even using a very low cutoff of 150 EV, we are still only making an error below 1%. And if we compare the computational time, while here it takes 400 seconds, if we would use, say, a safe value of 520 EV, it would take 3,000 seconds. Yeah. So it is quite a significant speed up. We're talking about 8 times speed up, and also the amount of memory that is required for this calculation. So in this plot on the right, I show the value of the mobility. The axis is on the left, and on the right, the computational time. So as you increase the cutoff, naturally, the computational time just increases always. But you see that after, at some point, increasing the cutoff doesn't change your final value. And so the optimal region for this particular case is actually 150 EV, which is even below the E and max that you would find in this in the pod car. You are still below 1% error, and you can run 7 times faster. So this is very important. Another in-car tag is ENCAT LR, so that's also a cutoff, but for the treatment of the long-range part. Again, the mobility doesn't change significantly. Here we are always below 1% error. You see that the computational time does increase significantly without much of a benefit in the accuracy of your calculation. So again, we should just use the lowest possible value of ENCAT that doesn't change significantly the final value. Another in-car tag is transport NIDOS, which I mentioned in the case of Closed-Legendre integration, so L transport driver 2. I show different values of transport anidos on the left. And we can see that beyond 250 points, the mobility doesn't change anymore. So why should we continue increasing the number of points if we are only increasing the computational time without changing the final value of the mobility? So in this case, the optimal setting would be to use 151 points for the energy integration. And last but not least, this is actually probably the most important in-car type or most important input of the calculation, K-points ELF, that determines the density of the mesh used to compute the electronic lifetimes and to compute the transport distribution function, which enters in the computation of the Onsager coefficients and transport coefficients. So here I show K spacing, so that's the minimum distance between K points, and the lowest value means denser K point mesh, and I show values of mobility. Here the error is quite large, so using very coarse grids changes a lot the final value of the mobility that you get. So you really need to go for very dense meshes. So it's critical to look at the convergence, but of this parameter, and the computational time increases really very, very significant. What I recommend in this case is to try to extrapolate the quantity that you are interested in, the mobility in this case, to infinity. So just use the two points between different samplings, and just a simple formula to extrapolate to infinite sampling. And you will see that eventually your value also stabilizes. It doesn't change anymore. And so you know that you are obtaining a reliable result. So final words for the performance. Tune the performance critical in-car tags. Don't just use large values because it's safe. You will be wasting computational time. And in the end, you might not be able to reach the accuracy of your calculation just because you are spending computational resources in something that doesn't make a difference for the final result. This can lead to 10 times speed up or more. If you combine all of this, you can make really poor choices that make your calculations not feasible. Keep in mind that temperature and doping increase the transport window, and that also changes significantly your computational time. Avoid high temperatures or high doping values if you don't need them. And put computational effort in the in-car tag that changes the results the most. I mean, normally K-points ELF. So that's it for the computational part. Now I will show you quickly some applications. So one of them is the conductivity of BCC iron. You will look at this example in the tutorials. The simplest approximation that one can use for computing conductivity is the constant relaxation time approximation. And here I show a plot of the conductivity as function of the K-point sampling. The red line is the experimental value. You can see that we are just slightly underestimating experiment. But this constant relaxation time, of course, it's a parameter that we put in the in-car file. So we can just change it and we would get the value on top of experiment. So that's not meaningful by itself. But even under this approximation, we should not forget that iron is magnetic. So we should perform a spin polarized calculation, setting spin 2. And that, of course, will change already our result. So we are already slightly above experiment. If we go beyond this constant relaxation time approximation and we use self-energy relaxation time approximation, these are the values that we get. So before we were in this teal line, and now we get this purple line. So we are above experiment, way above experiment. So we have a better agreement when we were doing constant relaxation approximation. What is happening? Let's look at the lifetimes. So here it's different lifetimes that we needed to compute that enter in the transport distribution function. The horizontal line is the transport relaxation time that is set by default in the in-car tag, in the in-car file, and is 1e to the minus 14 seconds. And what we see is that the lifetimes computed from self-energy relaxation time approximation are higher than the constant relaxation time that we set. And that, of course, means that the conductivity will be higher too. But in this example, we were using the relaxed lattice parameter from PbE. Let's try using the experimental one. So this green line is the relaxed PbE lattice parameter. And now when we use the experimental one, we obtain this teal line and this purple line. So these are using different pseudo-potentials as well. So the purple is using the standard pseudo-potential and the teal is using the GW pseudo-potential. So that is another important aspect to consider, which pseudo-potential we use. The GW ones are more accurate, so I believe that the result is going to be closer to the experiment. So it's more reliable, at least, even if it's not closer to experiment. We can also try using different functional, say LDA. So here it's a comparison using the standard pseudo-potential with PbE, the purple line, or with LDA, that's the blue line. We should extrapolate to infinity, as I mentioned before. And there, what we see is that if we use the GW pseudo-potential, so the teal line and the red line, we are very close to experiment using the experimental lattice parameter. If we use the lattice parameter, the PbE lattice parameter, then we're not so close to experiment. So this is something to consider when performing these calculations. Lattice parameters, pseudo-potentials, exchange correlation. Another case, one can look at this mobility of semiconductors. So the conductivity is proportional to the carrier density. It can be computed using this formula, so that this is already replacing the Onsager coefficient and obtaining directly the conductivity. And what one does to compute the mobility and to define an electron or a hole mobility is to split the contributions. So here we have a sum over bands, and we split the contributions into conduction band and valence band. And by defining that, we can obtain an electron mobility. So that is just the conduction band contribution to the conductivity divided by the number, so the electron carrier density, which is computed using this formula here. And similarly, the electron hole mobility, it's done by computing the conductivity, including only the valence band, and dividing by the number of hole carriers. So one example is the transport of gallium arsenide. It requires a very k-point mesh, a very dense k-point mesh to converge, but the energy window is very small around the chemical potential. Here it's a convergence plot with respect to number of k-points in the irreducible Brillouin zone. The different colors are using different supercell sizes to compute the electron-phonon potential, and we obtain a mobility of 7,045 centimeters square per volt per second. And the results with Abinit are very, very close. Here's another example, can compute it with VASP, just obtaining mobility of different semiconductors, either for electron, so it's either electron mobility or hole mobility. This is the same selection of materials as this paper, this reference one. And the electron-phonon potentials are the same ones that were used to compute the 0.3 normalization. This is used using relaxed lattice parameters. What we are showing in this plot is the calculated mobility versus experimental mobility. And we can see that the agreement is quite good. In general, PbE is used except for carbon boron nitride, aluminum nitride. where LDA is used. These are the parameters of the calculation. So roughly 120 by 120 by 120 K point sampling. And we have the treatment of the long range part, but no quadruples. So the average error is about 30%. So we do get close to experimental values. Of course, the experiments themselves also have some variability. And the largest relative error is for aluminum phosphide, the electron mobility. For thermoelectrics, let's look at lead selenide and lead telluride rock salt structures, which are commonly used thermoelectric materials. So here are just some images of the lifetimes for these two materials. The density of states, it's in blue. In green is the transport distribution function, and in red is the chemical potential. So these are all VASP calculations. These are some meters that were used to run the calculation. We can obtain electrical conductivity and compare with experiments. The agreement is good. Of course, we are not considering other scattering mechanisms such as defects, which do play a role in these materials, especially when comparing with experiments. We can compute the Seebeck coefficients and the electronic contribution to the thermal conductivity and the experimental data. Then once we have all these transport coefficients, we can determine as well the ZT figure of merit. This figure of merit, it's basically how good the material is at converting heat gradient to electric current or vice versa. So either Seebeck effect or finding materials with high ZT is of course interesting for improving the efficiency of these applications that I mentioned before, like coolers or radioisotope generators. But it can also be used to recover waste heat. So for these materials, like telluride and selenide, we do get again, fair agreement with experiment. We can use different exchange relation functions, PbSol or PbE. The lattice thermal conductivity in this case was computed with phonon 3pi, but we could also use Le Plata method inside VASP, for example. At the moment, we try to compare with experiments, but we have a first principle school that can compute these quantities, then we might want to find better thermoelectrics using really fast principles calculations. So in conclusion, we can compute electronic transport properties, including electron-phonon scattering from first principles. This is useful for benchmarking of DFT methods. So we can compute transport properties and compare with experiments. And this is a reliable benchmark for DFT. So because it requires good band gaps, effective masses, dielectric tensor, Born effective charges, and a phonon dispersion. So if we are able to get good agreement experiment, that means likely. At least the description of the electronic band structure should be good in order to be able to get good agreement. But also materials discovery. So if we can compute these quantities from first principles, we can use this as a design parameter. So we can say we want to optimize the mobility. What changes do we need to do in the structure to optimize certain parameters? And this can be integrated into automatic workflows, or at least that was one of our design goals, is to have a same input file to be applicable to many materials with minimal human intervention. So, and a final advice, please converge your calculations to save computational resources and save your own time waiting for this calculation. So I would like, of course, to thank this work was not done just by me, it was done by all these people, in particular Laurent Chaput, Manuel Engel, Atsushi Togo, Martin Schlipf, Martin Masman, and Guillaume Cresse. And I would like to thank you for your attention.
Brilliant. Thank you very much for the talk, Henrique. You've put it all together in a way that's quite accessible. Transport calculations are not necessarily simple, and there's always a lot of convergence tests to do. So thank you for presenting it so succinctly.